Hello from Chem Help ASAP. Let's discuss some data-driven methods that are often helpful for lead optimization. After watching this video, students will be able to describe the single-point modification approach to lead optimization and describe matched molecular pair analysis as another approach for lead optimization. There are a few methods or approaches for teasing trends out of structure-activity results. Two of the most frequently encountered methods are the use of single-point modifications and matched molecular pair analysis, or MMP analysis. Both are methods for trying to control for variables and accelerate the lead optimization process as much as possible. Let's talk about both methods. I sometimes call single-point modification the divide and conquer method. Let's see how this works. Assume that this molecule in the upper left is part of our lead series. In a sense, the molecule has two parts, the left ring and the right ring. Often researchers will describe parts of a molecule with compass points. So the western ring and the eastern ring. Using single-point modification, one member of the discovery team might make a number of different analogues of the western ring while leaving the eastern ring unchanged. Let's say we want to look at R groups at this position relative to this R prime group. Here are four possible analogues with their activity. The R group, the best one, is a methyl, which gives high potency. So let's circle that methyl. Note that the R prime group is the same for all four compounds. R prime is a hydrogen. Simultaneously, another team member would make analogues of the eastern ring with R groups off the western ring unchanged. Here are some results with the chloro being the best R prime group. Based on these results, you'd expect this molecule, R equals methyl on the western ring and Cl on the eastern ring. This is the most potent compound, or that's what we predict. Instead of making all 16 possible analogues, all possible combinations of R and R prime groups, we save just a bit of effort. Leads with 3 or more regions of modification provide even more time savings through single-point modification. Matched molecular pair, or MMP analysis, is used to compare both different scaffolds and substituents off the scaffolds. MMP analysis requires a set of compounds to have already been prepared and assayed for activity. So here are 8 compounds. Among these compounds, we have 2 different scaffolds. The quinoline with 1 ring nitrogen and the quinazoline with 2. We also have some different substituents around the ring. In a matched molecular pair analysis, you would look over this set of analogues and look for pairs of compounds that differ in one detail. Compound 1 and 2 differ only in the scaffold. Compound 2 has an extra nitrogen. Compound 1 and 4 differ by the addition of a methyl. The same is true for 2 and 3. They differ by an additional methyl. By comparing these matched pairs, these matched molecules in a pairwise fashion, researchers can tease out trends over which scaffold or R groups give rise to the best activity. Of course, activity is defined broadly as potency, efficacy, ADME, PK, or safety. Both the single-point modification approach and the matched molecular pair approach rely on a key assumption: the ligand-target binding orientation, sometimes called the binding pose must be consistent across the different lead analogues being compared. If the addition of a new group drastically changes how a molecule interacts with the target, then trends in the comparison of activity will likely be difficult to discern. If the comparisons do not seem informative or show inconsistency, then the binding orientation may be changing in an unanticipated manner. We have described both single-point modification and matched molecular pair analysis as two approaches to help facilitate lead optimization. I hope you have a better understanding of the ideas of matched molecular pairs and single-point modification. Questions are always welcome in the comments section below the video. Take care.